Hello, my esteemed viewers. Welcome to my channel, Dr. J's Physics Lecture Series. I'll be looking at statics in this particular lecture series. I might add one or two things regarding friction. Okay, so what is statics? I'll just briefly write that as I say it. Statics is actually a branch of mechanics that deals with bodies in equilibrium, or say bodies at rest. So we can say statics deals with objects at rest, objects at rest, or forces in equilibrium. Say some few things, then we'll look at some problems. When we say equilibrium, we're actually talking about a system at rest. Okay, so an object is in a state of equilibrium if that object satisfies every condition pertaining to equilibrium. In the case of mechanical equilibrium, we have two conditions to be satisfied. That the vector sum of all the external forces acting on the body must be equal to zero. I take that again. For mechanical equilibrium, we have two conditions that have to be satisfied. First is that the vector sum of all the external forces acting on that body must be equal to zero. Then we also have a case whereby the vector sum of all the external torque acting about any point on the body must be equal to zero. Take that again. The vector sum of all the external torque about any point acting on an object must be equal to zero. The first one that has to do with the vector sum of all the external forces acting on an object must be equal to zero is termed translational equilibrium. While the one that has to do with external torque is referred to as rotational equilibrium. So a body that satisfies the above two conditions are said to be in mechanical equilibrium. If the body is at rest, we say it is called a static equilibrium. It means the body is in a state of static equilibrium. But if the body is in motion, then the kind of equilibrium is referred to as a dynamic equilibrium. So, having understood this, let's just take two problems involving statics, then a particular problem involving friction for this particular series. So we have a problem here. An object of mass 10 kg is supported by two strings, which makes angles of 52 degrees and 38 degrees with the vertical. Calculate the tension in both strings. Now, we can visualize this problem by a simple sketch. Take note of every detail in the question. An object of mass 10 kg is supported by two strings. Those two strings are making angles of 52 degrees and 38 degrees with the vertical. Take note, not with the horizontal, with the vertical. So, assuming this is the object, this is the object, this is like the vertical. The object is making 52 degrees, the strings supporting the object One is at 52 degrees to the vertical. The other is at 38 degrees to the vertical. Of course, this can be like this. Since it is hanging, we can just take this off to avoid confusion. So this is just a schematic of this problem. We can as well use a free body diagram to illustrate this very well. So if this is a free body diagram to illustrate this scenario, I can say this is the box, this is the box, this is the vertical. Permit my line is not straight. We have one of the strings holding this box is at, this is a string, is at 38 degrees with the vertical. The other one is at 52 degrees with the vertical. Once you are able to represent the information correctly, then you have no problem solving. So we draw x component for both forces. Let's call this one T2. Let's call this one T1. They both have y component, so this is y1, and they both have, this one has y2 as a component. The x component is x2 here, and that of this is x1. Of course, the weight is acting downwards. So with this, come back, what are we asked to find? The tension. We just apply our knowledge on forces. First and foremost, let us find the components of the tension, that is both tensions, along the x and the y axis. So we have x component for the tension T1, y component for the tension T1. Then we go to x, y, T2, we get the x and the y component respectively. Now take note that our weight is always mg. So for the first tension T1, we have that if here is 38, it implies that here will be 52 degrees. If this angle to the vertical is 52, then it implies that here will be 38. So we are working with this triangle. So let's say for the first, for T1, which is this, let's find the y component. Since we are looking for the y component, we make use of this y component and the tension T. And this is the angle facing the y component. So this is opposite over what? Hypotenuse. And that gives us sine. Remember this. So if we proceed, we say sine 38 is equal to y1, that is opposite over hypotenuse T1. So our y1 is equivalent to T1 sine 38 degrees. Let's call this one equation 1. Then we look out for the x component for this same tension T1. So for the x component, we are going to work with this and the tension. So this is adjacent and hypotenuse. So we say cos 38 is adjacent, which is x1, all over the hypotenuse, which is t1. So our x1 is t1 cos 38 degrees. Let's call this one equation 2. Then we move on to y2. I'm going to replicate that figure here so that we can work with it. We had something like this. This is the vertical. This is 38 degrees. This is 52 degrees. So here is 52 degrees and here is 38 degrees. This is the weight acting downwards. Remember, this is T2 with Y2 component X2. This is X1 and this is Y1. This is T1. So we proceed for T2. So for T2, let's find both the X and Y component. So for the Y component of this tension T2, we can say that sine 52 is equal to opposite Y2 all over hypotenuse, which is T2. So Y2 is T2 sine 52 degrees. Let's call this one equation 3. Then for the X component of T2, we can say that cos 52 is equal to x2 all over t2. So x2 is equal to t2 cos 52 degrees. Let's call this one equation 4. So what we do, we sum the tension, that's the forces along the x direction and the forces along the y direction. So every force in one direction we sum together and every force in the other direction we sum together. So for the x component, let's say sum all forces. Sum all forces in the x and y directions. For the x direction, we have that T1, we've done that in the previous slide, T1 cos 38, that is for T1, is equal to that of T2. T2 is, the S component is T2 cos 52. So say T2 cos 52 degrees so if we bring all of them to one side of the expression, it becomes T1 cos 38 degrees minus T2 cos 52 degrees, which is equal to 0. Then in the y direction, add also. So for the y direction, we have both upward force and downward forces. So the sum of the upward forces is equal to the sum of downward forces. So if that is the case, we say that T1, we are going to add up the upward force. So we say Y1 plus Y2 is equal to W. What is Y1? Y1 is T1 sine 38. So T1 sine 38 plus Y2. Y2, this is Y2, T2 sine 52 is equal to the weight, which is 9.8 times 10. Which is 98. So our T1 sine 38 degrees plus T2 sine 52 degrees is equal to 98. Let's call this one equation 5. Okay, we'll call this equation 5 and call this equation 6. Or we can use the first one as 5 to make it more easier for us. So from equation 5, you see we've already gotten expressions for T1 and T2, but we can't proceed with this, so we'll have to eliminate one. So from equation 5, that's this equation, we can say that T2 is equal to T1 cos 38 all over cos 52, which is equal to T1 times cos 38 is 0.7880, as to 4 decimal places. Cos 52 is 0.6157. So that our T2 will give us T1 times whatever we have, which is 1.28 T1. So let's call this one equation 7. Move on to another slide. So if we move on, we substitute or just recall that T1 sine 38 plus T2 sine 52 is equal to 98. So if that is the case, and we have that T2 is not equal to 1.28 T1, all you need to do is substitute this into this expression. So that gives us T1 sine 38 plus, where we have T2, replace it with 1.28 T1. So 1.28 T1 sine 52 degrees equal to 98. So we evaluate. This gives us 0.6156 T1 plus 1.0086 for T1 equal to 98. They are both containing T1, so you add, so we have 1.662424 T1 equal to 98, so that T1 will be 98 divided by 1.62424. That gives us 60.3359. So we can approximate T1 to be 60.3 Newton. To calculate for T2, we already know that T2 is equivalent to 1.28 T1. If that is the case, then T2 will be equal to 1.28 times 60.3 Newton. This gives us 77.184. So that we can say our T2 can be approximated to 77.2 Newton. So you see how easy it is to solve this problem. So we have a problem involving friction here. We have a 20-kilogram box being pulled along the level ground by a rope, and that rope is inclined at an angle of 30 degrees above the horizontal. The coefficient of friction between the box and the ground is 0.20. How large is the pulling force if the box is moving with an acceleration of 0.4 meters per second? Well, it's quite easy. Just get a diagram to illustrate the condition. This is the box. Being pulled along a level ground. Okay. This is the level ground. So we draw a normal force. This is weight. The box is being pulled at an angle of 30 degrees above the horizontal. So this is the force. This is the normal. Of course, we are given the value for the coefficient of friction. So friction is acting on this box, and the friction will act in a direction. The frictional force acts in a direction to oppose the motion of the object. So that direction has to be in the opposite direction of the object. So this is the coefficient of friction, or the force of friction rather. So if we apply equilibrium of forces using equilibrium of forces, we can say for the x component of this block, this is the force. You can see the force. So we can have the x component and the y component. For the x component, we say that cos theta, because we are looking for the x component and we have the force here. So this is adjacent and hypotenuse. So we use cos. Adjacent and hypotenuse, we use cos. So we say cos theta is equal to x over f. This implies that x is equal to what? F cos theta. So this x is f cos theta. Now we recall again that f is equal to ma. Always remember this. Now, since the acceleration of this block, the block is accelerating towards this direction, so it means the force along this side, along this direction, will be greater than the frictional force. And so, since, let's write that down, since the acceleration of the block is along positive x direction, the total force on the block is, now because it is moving along this, moving towards this direction, it means this x component of the force is greater than the frictional force. So we say F cos theta minus the frictional force is equal to ma. So that we can say the frictional force is the same thing as saying F cos theta minus ma. For the y component, we can say that sine theta, why are we using sine? We are looking for the y component and we have this value here, which is f. So we are using this side and this side. So this is hypotenuse, this is opposite. So opposite over hypotenuse is sine. So we say sine theta is equal to y over f. This implies that y is equal to f sine theta. So if we balance the forces acting in the vertical direction, the forces acting in the vertical direction are y and n. That is upward. We also have the one acting downward. So we say that balancing the forces, I'll use another slide for that. Okay, I can use here. Balance the forces in the vertical direction. If that is the case, it means the sum of the upward forces will be equal to the sum of the downward forces. So we say y plus n is equal to w. Our y is f sine theta. So we say f sine theta plus n is equal to mg, because w is mg. So from that previous equation, our normal n is equal to mg. Or let me recall that other equation since this is a new slide. Say recall f sine theta plus n equal to mg. This implies that n can be expressed as mg minus f sine theta. Now, the force of kinetic friction so recall the force of kinetic friction is given by F or just simply say force of friction, still the same thing. So we can then say because remember from the previous slide we had the expression for the force of friction, which is F equal to F cos theta minus MA. It's in the previous slide, so you go back to the previous slide, you see this equation, though I didn't number them. And now we are saying that F is also equal to this. So it means we can equate both of them. So if we do that, we say F cos theta minus MA is equal to this. And we had previously got N. This is the equation for N. So we can do a smart substitution. So we say F cos theta minus MA is equal to this into mg minus F sine theta. If we expand, we have F cos theta minus MA is equal to this minus so that if we evaluate this, we have that F cos theta plus F sine theta is equal to plus MA. So our F will now be equal to this. Of course, we can factor out F first of all. We can say F into cos theta plus this is equal to so when we proceed, we can evaluate our F to be this mg plus ma divided by cos theta plus mu sine theta. So if we evaluate, just substitute all the values of this into the equation, we are going to get our coefficient of friction is 0.2. So say 0.2 multiplied by 10 multiplied by 20 plus 20, which is the mass, times 0.4, which is the acceleration, divided by cos theta, that is cos 30 degrees, plus 0.2 times sine 30 degrees. You evaluate this separately. When you do that, your force will give you exactly 49.689 Newton, which we can approximate to 50 Newton. So we have come to the end of this particular lecture series. Remember to subscribe to my channel for easy updates and notifications when I upload new videos. Please remember to send your comments in the comment section. They'll be responded to. Thank you.